Alrighty, folks. We're starting our first vectors lesson here. Um, and I'm actually pretty excited that we don't get to do this very often in math classes, but I've actually been able to secure a guest speaker to help introduce this topic. So, Mr. Guest Speaker, would you like to introduce yourself?
Go by the name of Vector.
Wow, kids, can you believe it? The main antagonist from Universal Pictures' 2010 classic Despicable Me, Vector. He's here, right in our digital classroom. Hey, Vector, you seem like an expert in the area. Can you help explain what is a vector?
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude.
Wow, well, I can't say that I co-sign that whole crime bit, but I can say that, yes, for sure, that is a good description of what a vector is. So a vector is a mathematical, I'd like to say object. Maybe it's the computer scientist in me. With both direction and magnitude. So what that means is we're going to have something that, I just changed to my grade 9 geometry. That's fun. We're going to have something, we're going to basically be treating these objects that contain two pieces of information simultaneously. They tell you which way it's pointing, and they tell you its magnitude, which is just a fancy word for a size or a length. And often we represent vectors with an arrow. So that vector is however long that is, that's its magnitude, and it's going in that direction up there. So this is sort of the first time you're going to experience this where in math, it happens quite a bit in higher level math, where we introduce these new types of things that aren't necessarily just numbers anymore. So this is two things. It's a number with a direction attached to it. And we see how they behave, and can we define certain things? What will it mean to add these two things, because they're not quite numbers anymore? What will it mean to subtract? Can we multiply them? Will they behave in the way we expect them to behave? And then we'll use these things to sort of represent other things. So vectors get used quite a bit in physics. So in the real world, velocity is a vector because velocity includes both how fast you're going and which direction. Displacement is a vector. It's how far you've gone and which way you went. All forces are vectors. And I believe weight is a vector as well. So that changes based on, that's the force of gravity. So your weight changes depending on where you are. If you're in space, you're weightless, so on and so forth. But that is it has a direction. Your weight is down towards the ground when you're on Earth. A scalar is the sort of opposite of a vector. It's just a number. No direction attached to it. Just a size, no direction. So in the real world, that would be things like just speed doesn't have the direction, just distance doesn't have a direction attached to it. I believe mass is the directionless weight. So those are real world scalars, but anything that's just a number is referred to as a scalar. When we write vectors to show that a vector is a vector and not a scalar, to show that it's got these two pieces of information, we'll use whatever its variable is. So maybe we use v for this vector, and we put a little arrow over the top of v. So just that type of arrow over v, that denotes that it is a vector. That's how you do it when you're writing by hand. If you're reading through a textbook or whatever, some textbooks, instead of using the arrow notation, will just have v, but it would be bold. So if it's typed in if a variable is typed in a bold setting and they're switching back between bold and unbold letters, the bold letters are vectors and the unbold ones are just scalar vectors. So that's really annoying. I don't like it when books do that, but it is something to look out for. When you're in university, if you're taking, say, a course on linear algebra, your textbook might do that, where if the variable's in bold, it means it's a vector. So the magnitude of a vector is its size or length. You can think of it as that. And for notation, if that's the vector v, that is the two absolute value bars is what you've seen them before. We're now going to say that's magnitude bars. So when there's a vector inside, that's saying just the magnitude of that vector. So we're going to ignore the direction and just keep the magnitude. So the magnitude of a vector is a scalar. It's just the number. And then I'm going to go over some definitions. So two vectors are equal if they have the same magnitude and same direction. So that's what it takes for two vectors to be equal. So this vector and that vector, let's say, would be equal vectors. They are the same length, or I tried to make them the same length, and they're pointing in the same direction. And maybe I'll take this opportunity to point out that vectors have a magnitude and a direction. They do not have a location in space. So no matter where I draw, if I'm drawing an arrow that's that long in that direction, it is the exact same as every other vector that's that long in that direction. It doesn't matter where on the page you place it. They're always equal to each other. Opposite vectors have the same magnitude and opposite directions, so completely flipped. So one going this way, one going that way, but they have to be the same magnitude to be considered opposite and flipped completely 180 degrees. So take the arrow, put it on the other end of the line. That's basically what we're going for. Parallel. Parallel just refers to two vectors that have the same direction, but also opposite direction. So they're kind of on the same line. Doesn't matter which way they're going on that line. And magnitude here doesn't matter for parallel. So those would all be considered parallel vectors. No, that's all I'm talking about, I guess. So that's just the intro here. So just getting used to this idea that vectors have both a size and a direction. We've got these three definitions: equal, opposite, and parallel. If we're doing magnitude, you put the absolute value bars around is how you do it, but we would read that as the magnitude of v. We wouldn't say the absolute value of v. It's using the same symbol because absolute value bars just give the size of a number. It doesn't matter which way on the number line it's facing. It's -5 and +5 both have a size of 5. So absolute value of 5 as well. So that's why it's using the same symbol. I guess I should point out, if I'm talking about other textbooks, sometimes they'll do, for magnitude of a vector, sometimes they'll do 2 sets of bars instead of 1. But I'll use the 1 in all of my stuff. But both mean the same thing. So in this exit card, I've drawn this perfect. It's supposed to be a parallelogram, so assume opposite sides are in fact parallel and the same length. I want you to find as many examples of equal vectors, opposite vectors, or parallel vectors that you can. Use only the vectors I've drawn here. So I've put arrows on them. So I've got the vector AB, and that's how I would represent that vector. The vector that starts at A and goes to B. So that gives me the direction. But BA, this one, is not drawn in the picture. So try and use only the vectors I've drawn to try and come up with a list of equal, opposite, and parallel vectors. And I believe I've got the answer to this listed with the practice question answers as well at the bottom. And then there's some extra practice that we can work on in class. Yeah. And the exit answer is down there, so don't peek. Okay. What do you think? Was that a good lesson?